Hi, I'm Adam Pearson.
And I'm Jacob Bransky. We are students at Carleton College that are learning about special relativity.
Today, we want to introduce to you guys the theory of special relativity, as well as solve a paradox involving taking a picture of an object moving close to the speed of light.
First, an introduction of special relativity. There are two principles to special relativity.
One, the laws of physics do not change.
Second, the speed of light is always constant.
As an object increases velocity to reach speeds close to that of light, to a person at rest, the object seems to be contracted and shortened.
In this picture, we see three rocket ships. The closer a rocket ship gets to the speed of light, the more its length contracts.
This is because, as stated before, the speed of light is constant.
Because the speed of light is constant, and the rocket ship is moving very close to the speed of light, the light particles emitted from the front of the rocket ship do not move away from the rocket very fast.
Consider you sitting in a car to be like the rocket ship and a semi-truck to be like a light particle.
If you are at rest in the car and see a semi-truck whiz by you, it will appear to be moving very fast. This is the way you normally see light on Earth.
However, if you are both driving down the highway, as a semi-truck passes you, it does not appear to be going very fast.
This is like what happens to the rocket ship in light once the rocket ship is going very fast.
Our paradox deals with the dilation of light.
A squared grid, like the one pictured, travels at 3/5 the speed of light. We will define the time equals 0 to be when the center of the grid passes our camera. At time equals 0, we will take a picture.
Due to length contraction and the constant speed of light, the squared grid will be distorted. Our question is, how will the squared grid look in our picture?
Let's say that our camera is 1 meter away from the center of the grid at time equals 0. Because of the constant speed of light, we will see the light waves that are exactly 1 meter away from the camera in all directions.
This will cause the camera to see the light at the edge of a 1 meter radius hemisphere.
In actuality, when we take a picture, we are only seeing the light waves in a hemisphere as well, but the objects we normally capture are not moving near the speed of light.
The problem is, our object is moving near the speed of light. So the locations that are captured by the camera will not be at t equals 0 for all 9 points because it takes time for the light to reach that hemisphere.
For point I, the center point, we are taking the picture when the point passes the camera. Therefore, point I will be 1 meter away and seen at the coordinate point 0, 0.
For A, C, D, E, G, and H, we will be seeing them in the past because their distances from x equals 0 will mean it takes time for the light waves to reach the 1 meter hemisphere. Therefore, we will see the light particles of the point in the past, so it will be seen further behind than it actually is. This causes all the points to be seen further left than they actually are.
This will cause the grid to look like this.
We must also address the points that are not on the line y equals 0. So A, B, C, E, F, and G will be seen from a time in the past because of the distortion from y equals 0 as well.
This will cause the grid to look like this. When we combine these two grids, we will get an image like this. Using the Pythagorean theorem, we found the exact coordinates for each of the points. They are shown on this diagram.
As you can see, an object moving near the speed of light will have a length contraction solely in the direction of movement.
Even though we do not see this in everyday life, ideas like this are very important when dealing with high speeds and great distances often dealt with in space.
Thank you for your time. I hope you gained some understanding of the theory of special relativity.
May the science be with you.